Welcome to Thought Kernel, where we break down educational concepts to understand them deeply and their applications in the natural world. Today, we're going to be going over Taylor's series, a key concept in early calculus for high school and college level students. Picture yourself standing on a mountain, but everything around you is covered in fog. You can't see more than a step in any direction. No cliffs, no peaks, no valleys. Just a bit of ground right underneath your feet. Now imagine someone asks you, can you draw the shape of the whole mountain? Seems impossible, right? But here's the twist. If you know how steep the ground is under your feet, how fast the steepness is changing, and how that change itself is changing, you actually can start predicting what the mountain looks like. In math, this idea is real. It's called the Taylor series. It lets you reconstruct an entire function, even the most complicated ones, just by knowing how they behave at one single point. Now, zooming into the function. Let's switch from the mountain to something simple, a graph of a function. Let's say you know the function's value at a point. We'll call that point a, or function f of a, as shown. That gives you the height of the curve. Next, imagine drawing a straight line that just barely touches the curve at that point. That's the tangent line. It tells you the slope. Is the function increasing or decreasing? Now go one level deeper. How is the slope changing? Is the curve bending up like a smile or down like a frown? That's the second derivative, and it adds curvature in parallel to the first derivative, which gives you the height as stated. If you go even further, you can see how that curvature is changing. This leads to more complex shapes and wiggles, followed by higher order derivatives. By combining all these pieces, value, slope, curvature, and so on, we build up a picture of the function step by step. Here, the function e to the power of x is shown by the red line. The color coordinated pieces in the middle photo highlight the lines. The green line is the tangent line, the purple line is the first derivative, the black line is the second derivative, and the orange line is the third derivative. Oh, sorry, I mean fourth derivative. Now, building a curve from nowhere. Essentially, we're going to be building a function out of thin air just from the single point as shown. The Taylor series is just this process written in math language. It starts with the value of the function at your chosen point, f of a. That's your first clue, your current position. Next comes the first derivative of a times x minus a linear approximation based on the slope. It tells you the direction the function is headed. Then comes the second derivative of a over factorial 2 multiplied by x minus a squared, which adds curvature, like bending the line into a bowl. Higher order terms, like the third derivative of a over 3 factorial times x minus a cubed, adds even more structure fitting towards the function. Together, they form a kind of infinite polynomial that tries to match the original function as closely as possible, all using just the derivative at one point. Each term helps the approximation hug the original curve a little more closely. As you can see, each colored derivative up to the fifth would add 5 terms to the Taylor series polynomial created. That would then allow us to mimic the function just from a single point. Now, approximating sine. Let's bring this to life with a familiar example, the sine function. Near x equals 0, the function sine of x starts off flat, just 0. That's your 0th approximation, a flat line. The first derivative is 1. So the next step gives us the line y equals x. That's already not bad. But sine is curved, so we add a negative cubic term. That's the negative x cubed over 6. Suddenly, we get a nice dip, like the sine wave. Keep adding higher powers of x, and the shape starts to ripple perfectly, just like the original sine function. You're rebuilding an infinite wave using just math from the point 0. So it's not only limited to 5 derivatives as shown. Going up to the orange and blue ones, I use the 7th and ninth derivative of the sine wave. The thing about Taylor series is you could go infinitely as many times until your function exactly snaps to the sine wave visually. Now, why it works. So, how is this even possible? The secret is in the derivatives. Derivatives tell us how a function behaves. The first one says, are you going up or down? The second one says, are you curving upward or downward? The third says, is your curvature itself changing? These layers of change are like instructions. If you give math all these instructions at a single point, it can start building a copy of the function nearby. The more instructions you add, the further out the copy matches. And for many functions, especially those that are nice and smooth, the Taylor series isn't just an approximation. It becomes the function. Now, any approximation after the third derivative, such as fourth and fifth, only reshapes the curve with what we earlier said were the wiggle movements. Not necessarily wiggles, but just small changes that slowly fit it to the correct function that we are attempting to model from the point. Now, Taylor series in the real world. You might think this is just a cool math trick, but it's everywhere. In physics, Taylor series are used to approximate forces, motion, and energy. In finance, they help model how the price of an option changes using a version called the Black-Scholes model, shown in the top right. In computer science, they power algorithms that need fast, accurate predictions. Furthermore, in machine learning, they're used to optimize the very models that power AI and research how they work. Anytime you need to make a good guess about the future and you have good data about the present, Taylor series are often behind the scenes. Now, what started as just a dot in the fog, a single point on the mountain, turned into a map of the entire landscape. That's the power of the Taylor series, taking the tiniest bit of information and from it, unlocking the shape of the universe. You don't need to see the entire mountain to understand it. Sometimes all you need is a point, and the math to make sense of it.